Okay, so this morning we'll be looking at the final topic in this chapter, which is connected sets and compact sets. So the idea of a set being connected, of course, we are only interested in sets and subsets of R. So a subset A of R is said to be connected if for any 2 points, any two numbers in A, call them R and S, and any 2 point, let's say X, between R and S, if this set A is connected, then X will belong to A. So the picture looks like this. So let me just put sort of random set here, and let's just call this guy A. So this is our set. It turns out this set A is connected, and the reason for that is because if I take any two numbers belonging to A, any 2 points, it doesn't matter where they are, any two distinct points, R and S, then notice that every single point between R and S, every single point in between, so these are your X's, also belong to A. If this is possible for every single R and S, so vary these red points. If this is always possible, then we say that the set A is connected. So let me give you an example of a set that is not connected, or we say it is disconnected, right? So for example, what about this? So this is your set B. It contains of these two pieces, or we will call them components. So why is this set B not connected? Because let's say I take a point R over here and a point S over here. Now you need to ask yourself the question, are all points between R and S belonging to B? And the answer is no. For example, all these points over here are not in B, but they are between R and S. So a set is connected, so we could say A is connected and B is not connected. We say it is disconnected. Okay, so that's pretty much all what a connected set is in the real numbers. Okay, so for example, if we take the interval, open interval AB, this is a connected set. Why? Because for any two numbers in A and B, well, if you have two numbers in open interval A and B, then that means that any number, for example, X between R and S, well, let's just say R was the smaller of these two numbers. Then we get A is less than R because R is in open interval AB. And we say R was less than S. So X is less than S. And S also is in open interval AB, so S is less than B. In other words, X belongs to open interval AB. Therefore, open interval AB is a connected set. So in the second example, this set A, which is open interval 0, 1, union 1 to 3, is not connected because I could take, for example, so to show that the set is not connected, you just need to give one example of a point that is between two elements of that set, but is not in the set. So for example, if I take the points 1/2 and 1.5, these two numbers clearly belong to A, but there's a number between them that is not an A. For example, 1. 1 is not an A, right? So A is not connected. And if you think about it, the connected sets in R seem to all have the property that they are an interval, right? It seems that the connected sets in R could only be intervals. And we'll see that in a bit. This third example, the natural numbers, the integers, the rationals, and the irrationals are all disconnected or not connected sets. Okay, so again, to show that any of these sets are not connected, you just need to find 2 points in that set and a third point between those two that is not in that set, right? So it's very easy to find for these 4 sets. These are not connected. In fact, we have a very nice classification of precisely what the connected sets are if you are in the real numbers. And that is given by this theorem. So the proof, we're not going to cover this proof, but this theorem is saying if A is a subset of R and A is connected if and only if A is an interval. In other words, the only connected sets or connected subsets of R are the intervals. So if you want to figure out whether or not a subset of R is connected, you just need to ask yourself, can I write that set as one single interval? Right? It has to be one single interval. Right? So basically the connected sets in R are any intervals. Right? Notice that the theorem doesn't tell you what type of intervals. It could be open interval, closed interval, half open, half closed interval, unbounded intervals. In fact, the interval minus infinity to infinity is connected, right? And if you're thinking, what is the interval minus infinity to infinity? Because that's an open interval. That's the real numbers. So the real numbers themselves are connected. Okay, because you can think of it, you can write the real numbers as minus infinity to infinity. Okay, so that's it for connected sets. So next we're going to move into compact sets. So in order to describe to you what a compact set is, so that's connected set, in order to describe to you what a compact set is, we need to first look at a couple different concepts. The first one is what is a cover, then what is an open cover, then we need to look at what is a subcover, and then I need to tell you finally what is a finite subcover. Okay, so we need to just look at what are these things. What is a cover? What is an open cover? What is a subcover? What is a finite subcover? So let me give you the picture of it, and then we'll go into the actual definitions of it. Okay, so again, all of this will be taking place in R, the real numbers, but I think it's better visualized in R squared. Okay, so I'm drawing all the picture in R squared, but of course we are just working on the real numbers, the real number line. Okay, so let's say I have this set A. So first let me tell you, what do I mean by a cover for A? So a cover for A is simply a collection of sets such that A is contained in their union, right? So very easy. So these green sets will be a cover for E, right? And I can have some sets out here. This is fine. Right? So, so we will then say that, so let's call these green sets AIs. Okay. So I would say that A is contained in the union of the AIs. Let's just say I is from some index set. In this case, we would say that the collection of the AIs is a cover for A, right? So a cover for a set is just a collection of sets such that A is somewhere in that union. And notice from this picture that I drew a couple things. Um, the sets that I drew could overlap. They don't have to be disjoint, right? Look, you see like there's overlap between them. That's fine. Some sets do not have to cover anything. Look, these guys out here, they aren't covering anything. That's fine. Some sets are inside other sets. That's fine. So a cover is something very, very general. It's not very, very restrictive at all. All that we require for a cover is that the set A be contained somewhere in the union of those guys, right? And it could be, well, the cover I drew here is a finite amount of sets in the cover, right? But there's no restriction as to how many sets has to be in this cover. There could be infinite sets we use to make a cover. Okay, so that is what a cover is. So let's go back to the slide. Okay, so let A be some subset of R, a collection, so script A or fancy AI, where I is some index set. So all this is saying is that this collection could be finite or it could be infinite, it could be countable, uncountable. It doesn't matter to us. It's just any collection of subsets of R. This collection is said to be a cover for A if A is contained in the union of it. Okay. Now, if it happens that each of these AIs, every single one of these AIs were an open set, then we say that the cover is an open cover. So what is an open cover? An open cover is simply a cover of A where all the sets you use in the cover are open sets. So that's an open cover, right? And if you're wondering, is could you talk about closed cover, where all the sets you use are closed sets? Yeah, you could talk about closed covers, right? But it turns out for the definition of a compact set, we require the open sets, not the closed sets. Okay, so that's an open cover. So what are some examples of this? So we could cover the real numbers with not just a cover, we could cover the real numbers with an open cover. For example, this collection of open intervals. So minus n comma n. So n range over all natural numbers. So when n is equal to 1, I get the open interval minus 1, 1. When n is equal to 2, I get open interval minus 2, 2. So minus 3, 3, minus 4, 4, and so on. Right? So all those open intervals. So it's an open interval, therefore it's an open set. And notice that the union of all these open intervals, well, these open intervals, each one is getting bigger than the previous. Okay, so the union of all of them as n from 1 to infinity, you could show very easily is equal to the real numbers. Okay, Notice that, let me go back to the definition for a cover. The definition for a cover simply says that the set A has to be inside the union of these guys. It could happen, so it's subset or equal to. It could happen that A might be equal to this union. That's perfectly fine. If A is equal to the union, that's fine. That's still a cover. So subset or equal. That's why you put the little line there. Okay, so in this particular example, the set we are dealing with, which is the real numbers, happens to be equal to this cover. Okay, so this is an open cover for the real numbers. Now, we can ask ourselves, if I give you, so now let's say I give you any subset of R, any set A, can you always find the covering for A? So if I give you, for example, this set A, and let's say A contain, well, I could only draw finitely many points. So let's just say A contains these 5 points. Right? Let's call them A1, A2, A3, A4, A5. But we could do this for any set, not just a finite set, any infinite set, we could do this. So here's what I'm going to do. I'm going to take each of these A's and put it in a set by himself. So A1, I'll put in a set by himself. A2, I'll put in a set by himself. A3, same. A4, same. A5, same. Okay, so every element of A, I put that guy in a set with just that element. Okay, what if I union all these guys together? What will I get? What if I union all of them together? That's just A, right? That's just A. In other words, A is equal to this union, right? So remember, cover means A is contained or it could be equal to. It's subset or equal to. So this means either strict subset or equal to. Okay. So in this case, this is a cover for A. So you could always do this. If I give you any set, if I give you any set A, you could always take every single element of A and put that element in a singleton set. And then collect all those singleton sets, and that will always be a cover for A. Okay. So every set has at least one cover. Right? This guy. Notice that this sort of covering is not an open cover. Why? Because the singleton set is not an open set. It's a closed set actually. Okay, so what about this collection? The collection n open interval n minus 1 over n, comma n plus 1 over n. So again, it's open interval, so it's an open set. It turns out that this collection is an open cover for n. Because if you think about it, all of these open intervals is a open it's a neighborhood centered at n of radius 1 over n. So this is just saying around every natural number, we're just going to put an open interval of radius 1 over n. Okay, so that's an open cover for the natural numbers. And if the set A happens to be an open set, then we could simply take for the collection the set A itself. In other words, so just like the second example, where if you give me any set A, I could always cover it by the collection of all singleton sets as those points range over A. If you give me any set A, I could always cover it by itself, A, because A is always a subset of A. So every set has at least two coverings. The one where you take every single element, so that's sort of like the finest cover you could get, or the largest of the covers. And the smallest cover you could get is simply just take the set itself, because you're just covering the set with itself. Okay. And if this set A is open, then this turns out to be an open cover because A is an open set. Okay, so what are the compact sets? So we did cover and we did open cover. That's simply a cover where all the sets is an open cover is an open set. So now I need to tell you what a well, we could talk about finite cover or finite subcover. So a finite cover or a finite subcover simply means the number of sets in in the collection you use to cover it is finite. So in this example of A, where I had A1, A2, A3, A4, A5, this is a finite cover of A. Okay, so a finite covering simply means the amount of sets you use to cover it is finite. Very easy. An open cover simply means the sets you used in the covering are all open. Okay. So what is a subcover now? A subcover, so notice in this example, this first drawing, a lot of these sets I don't need, right? There's a lot of these green sets that simply either did not cover any part of A, or they were covering a part of A that was already included in another set. In other words, maybe I could throw out some of these sets, right? So maybe I could throw out some of these sets. Maybe this guy here I could throw out as well. And I could still cover it. So a subcover means you have a cover and you pick out. So it's like a subset. But we were saying it's a subcover because it's just a cover, right? So it's a sub collection of the original cover that still does the covering. Okay, so that is what a subcover is. So subcover, put it here. So let's say we have a cover for A. If it is that let's say use S. So so now I'm taking a collection of AIs, but the I's are not ranging over this big I. They are ranging over, let's say, some set S, where S is a subset of the index set I. So this guy here is a sub-collection. Okay? This simply means just take some of these sets. You can take all of them if you want, right? We're taking some of these AIs. If A is still contained in the union of AI, this time I ranges are across S, not I, S. I think they use J. Let me just check that. So I'll be consistent. Okay, no, they use E. Right. Okay, so let's change this to E. So everything is consistent. Yeah, so they call So let's use the index set E. E, and they call this guy S. They call this guy E, right? So if it turns out that A is still contained in the union of the AIs where I now range over E, then we say that S is a subcover of A. Okay, so we have a cover for A, and a subcover of A simply means you take the original cover, take all those sets, and throw out some. If the remaining sets you have still could cover A, then we call that a subcover. Okay, so the ideas are very easy to understand, but you have to know how to write it mathematically. Okay, so suppose that script A is a collection of these AIs, and this collection is a cover for the set A. We say that a subcover, so fancy S or script S of A, is a subcollection of the original collection A that covers the set A. Okay, in other words, S is equal to the collection AI where I now range over E. And E is a subset of the index set I. So it means you don't need all the index of I, you just need E of them. And A is still somewhere in this union. Okay, so this is a subcover. So finally, what is a finite subcover? So finite just means there are just finitely many sets in it. It does not mean that the A's are finite, right? So the finite you see here don't mean that A1 is finite, A2 is finite, A3 is finite. No. It means that the number of A's that you have is finite. So a finite subcover is simply a subcover A1, A2, A3 up to AN. So in this case, we have N of them. So finite. That consists of a finite number of sets. So finite number of sets, not that the sets themselves are finite. So make sure you, you know that distinction. Okay, and now what is a compact set? So we have finite subcover. So compact means, so what does compact mean? A set is compact. A is compact or a compact set if every open cover has or admits a finite subcover. That is what a compact set is. A compact set means if you give me any, not just any cover, I don't want just any cover, I want the covers to only be open sets. So for a compact set, if you give me any open cover you come up with, I could always throw out sets from that open cover. I say you gave me too much. Okay? I could collect a finite amount of those sets from the open cover you give me. I collect a finite amount, so a finite subcover that still will cover it. Right? So if this is always possible for every open cover you give me, it's always possible to find a finite number of a finite collection of sets from that cover that still does the covering. We say that a set is compact. Okay. So a set A is said to be compact if every open cover of A has a finite subcover. Now I put here as a remark that proving a set is compact using this definition is usually very difficult. Why is it very difficult? Let's look at the definition. It's difficult to show that a set is compact this way. It's not impossible, but it's very difficult because you need to account for every single possible open cover, right? And there are so many different open covers I could do with so many different types of open sets. So I need to show that for any type, I could always refine that cover to get a finite amount that still does the covering. So that's why it's very tricky to do. Okay. Luckily, for subsets of R, there is an easier way to do this, right? And that's given by a very important result in analysis called the Heine-Borel theorem. So just like we saw at the start of the class when we were talking about connected sets, there was a classification of all connected sets in R. In the real numbers, if you are connected, you have to be an interval. Connected and intervals are the same in the real numbers. In a similar way, in the real numbers, there is a classification of the compact sets. That is Heine-Borel theorem. This theorem states that a subset of R is compact if and only if it is closed and bounded. In other words, if you are a compact subset of R, you must be both closed and bounded. Two conditions, closed and bounded. You need both of them. If you lose any one, no, you will not be compact. So if you are closed and bounded, you are compact. So what does this mean? This means now if I hand you some subset of R and I ask you, is this set a compact set? Right? You don't go, well, you could do it, you could try it if you want, but the difficult route is to then take an open cover, an arbitrary open cover, and try to find within it or prove that you could get a finite subcover. The easy way, that's the difficult way, is to use Heine-Borel theorem. The easy way is show that that set is closed, show that set is bounded. So bounded means it has a lower bound and it has a upper bound. You don't even need to get the supremum and the infimum, right? Because the supremum and infimum are special types of bounds. I just need a lower bound and an upper bound, bounded. Okay. So actually, not only R, Heine-Borel theorem works in R to the n. Okay. So the proof is omitted. You'll prove that later on in our next root analysis course. Okay, so this theorem basically tells us what all the compact sets in R look like. All you have to do is check whether the given set is closed and bounded. If yes to both conditions, then it is a compact set. It's a very, very, very useful theorem, so please remember it. And so we're going to use this theorem now to prove another big theorem in analysis, right, called the Bolzano-Weierstrass theorem. Now, this theorem may not seem very useful right now, but it has a lot of implication and is used in a lot of proofs later on, maybe not in this particular course, but you'll see it in other courses later on when you're talking a lot about, again, compactness and the idea of how compactness relates to sequences. Then they use this stuff a lot. Okay, so what is this theorem? It says that every bounded infinite subset of R has at least one limit point, right? So very straightforward statement. If I give you a bounded and it has to be infinite, so countable or uncountable, doesn't matter, subset of the real numbers, then you could always find in it a limit point. Okay, seems simple enough. So let's try to prove this one. This one we could prove. The proof makes use of the Heine-Borel theorem. Okay, so it's a proof by contradiction. So let A be a bounded infinite subset of R And what do I want to prove? I want to prove it has at least a limit point. So proof by contradiction means I'm going to assume that it has no limit points. So I assume A has no limit points. Now, if a set, so now let's think, if a set has no limit points, is that a closed set? Right? So if a set has no limit points, is it a closed set? So recall, what is it? Well, there are many different ways to think about a closed set. One of the ways to think about a closed set is A is closed if and only if A contains all its limit points. That is, if the derived set of A, which is the set of all limit points, is a subset of A. Okay, so again, this is the derived. This is sometimes called the derived set. It's the collection, it's a set of all limit points of A. Okay, so a set is closed if it has all its limit points. That's one of the ways you could think about a closed set. Right? Of course, a set is closed if it's the complement of an open set. That's another way. Okay, so the question was, if A has no limit points, what is the derived set? Well, then the derived set is just the empty set. A has no limit points, so it's the empty set. But remember, the empty set is always a subset of every single set. Okay, which means that the derived set is a subset of A, which means A is closed. Okay, so if a set has no limit points, it is closed. Okay. So another way to do it is to look at the closure. So I gave one way to show that A is closed. Here's another way. A set is closed if and only if it is equal to its closure. And remember, the closure is given by this thing A bar. So the closure is A union its limit points. And we said that the limit points is the empty set. So A union empty set is A. So we get A bar equal A. So A is closed. Okay, so A is a closed set, and we assume that A is bounded. Oh, great. Okay, so we assume A is bounded, and oh, yeah, it stays on the screen. Okay, let's get rid of that. Yeah, so we assume A is bounded, and we showed A is closed. So closed and bounded in the real numbers means, so now we use Heine-Borel theorem. So by Heine-Borel theorem, A must be a compact set. Okay, so very easy. A must be compact. So now I'm going to try to get a contradiction. I know A is compact. So since A has no limit points, every point of A is an isolated point. Remember, what is the difference between a limit point and an isolated point? A limit point means that any neighborhood around it has a point of A inside of it. Any neighborhood, no matter how big or how small you make it, you will always find points of A inside there. An isolated point means an isolated point is like the negation of a limit point. Isolated point means so you are isolated. This point is all by himself. An isolated point of A is a point belonging to A such that you could put a neighborhood around it that has no other points of A, right? So he's isolated. No other points of A is inside that neighborhood, okay? But A has no limit points. Therefore, every point must be an isolated point. The isolated point is the indication of the limit point. So that means for every element X belonging to A, I could find, or there exists, a radius, epsilon sub X. So this radius depends on X, the point, such that this deleted neighborhood around X of that radius, so remember deleted neighborhood simply means the neighborhood without the center. So if X is an isolated point, that means within this neighborhood, there is no other point of A. No points of A are in this neighborhood. Therefore, if I intersect this neighborhood with A, it should be empty, right? Intersection means, can you find an element in this neighborhood and in A? No. If you're an isolated point, there is no element. So this intersection must be empty, right? However, if I remove the deleted neighborhood, so if I add the center back to the set, will the intersection still be empty? So remember X. Where is this X from? Where is the center from? This X belongs to A. So if you add the center back to this neighborhood, you get the full neighborhood. X is in there. X is also in A. X is an element of A. Therefore, if now instead of taking the deleted neighborhood, you take the full neighborhood, that intersection will no longer be empty. It will contain one single point, the center. So that's what we're going to do. So you see now we remove the deleted neighborhood part, we take the full neighborhood. Intersection A only has one point, the center. Okay? So what we're going to do now is we are going to collect all these neighborhoods. So remember, this is a neighborhood for this particular point, X. A has a lot of elements. So let's collect together all these neighborhoods. So collect all these neighborhoods and put that in a collection. Okay, so for every element X belonging to A, find the neighborhood around it of that radius that has no other points of A inside of it. Collect together all those neighborhoods. But you know that the neighborhoods are open sets. So what is this collection? This is a collection of open sets. And notice that if you union all these neighborhoods together, you will cover A. Okay, why is this a cover of A? Well, it's a cover of A because if I take any element of A, notice it's in that neighborhood. Okay, so every element of A is in its neighborhood. Therefore, the collection of all these neighborhoods, the union of it covers A, right? So you're covering A with a bunch of these circles, bunch of these neighborhoods. So this is an open cover of A. But we know that A was compact, right? We proved using Heine-Borel A was compact. And we found an open cover. Therefore, there should exist a finite subcover. So there should exist finitely many X's belonging to A. So there should exist finitely many elements of A such that this now is a open subcover. So I am collecting from this original cover that may have so many neighborhoods in here. It turns out I don't need all these neighborhoods. I just need n of them, right? I just need n of them. So collect those neighborhoods. N with the center xi of corresponding radius epsilon sub xi, where I goes from 1 to n. So we have n of these neighborhoods. It turns out that I could still cover A with just n of them, right? So this is a finite subcover. So here's what we're going to do for the contradiction. I'm going to now say A is equal to A intersection this union. So what is this union? The finite subcover that I have here, I'm going to union them together. So these n neighborhoods, so let's say n was 5. Okay, so these 5 neighborhoods, union them together, right? But remember, these neighborhoods, they cover A. Okay, so A is somewhere in this union, right? A is somewhere in this union. Therefore, A intersection this union must be equal to A, right? Let me give you that written in another way. If A is a subset of B, then what is A intersection B? Well, if A is inside of B, then A intersection B is just A. That's the same thing here, except for B, we have the union of these neighborhoods. Right? So it's the same thing, but I'm using this guy for B. Okay? So that's the result we're using there. Now, you know that you have De Morgan's law that tells you how intersection distributes over unions, right? So we can move this intersection into the union. So move it into the union, and the neighborhood intersection A. We have a result for that. Let's go back. Look, it's the last line here. Each of these neighborhoods, when you intersect them with E, it's just the center of that neighborhood, right? And this is for this was for any one of those neighborhoods. But now I'm dealing with just n of them. I picked out n of them. Okay, so this is the same sort of neighborhood, but I just have n of them. So each of these neighborhoods, intersection A, is just the center, xi. Okay, so this innermost set, it's just xi. So I get the union of xi as I goes from 1 to n. So how many points are in this union? So the xi's are all different. So there are n points, right? The union of this set is just n points, x1, x2, x3, up to xn. They're just n points in this union. But this union I'm getting is equal to A. So A is equal to just n points? No, A was infinite. So this is the contradiction to A being infinite. Okay, therefore, what we assume from the beginning, we only assume that A has no limit points. Therefore, A must have at least one of these limit points. Okay, so that's the proof. Very nice proof. It brings together all of the ideas we learned so far. It brings together boundedness, closed sets, compact sets, limit points, unions, neighborhoods. So it all comes together in this nice proof. Okay, so make sure you know this proof. Right, so that's Bolzano-Weierstrass. Okay, are there any questions?